one, and I thought this was the best way to do it.
Which one's wrong?
Well, take your pick. Okay, so I'm going to talk about the Kochen-Specker theorem, and I presume it's very well known to people out here. So the motivation for this talk is essentially some work I did with Rob, which is about how to turn the Kochen-Specker theorem, which precludes non-contextual deterministic models of quantum theory, into an experimentally testable inequality, whose violation can actually say something about whether a non-contextual model of nature is possible, rather than the theory that we currently believe best describes nature. And of course, the motivation here is to take Kochen-Specker theorem as close as possible to Bell's theorem in terms of experimental testability. And the crucial ingredient here is that we are not assuming determinism. So this goes back to Rob's definition of contextuality, which Matt just talked about, where he generalized the definition to an operational theory, defined it for preparations and for transformations other than measurements. But then again, the analysis, the proofs in the paper were restricted to quantum theory. They were assuming quantum theory. Now this work does not assume quantum theory in that sense. So let me just start with this proof of the simple proof of the Kochen-Specker theorem. The original proof had required 117 rays in 3D Hilbert space due to Kochen and Specker. So this is an uncolorability proof. Essentially, what this means is that so this proof is due to Cabello et al. And it requires 18 rays in a 4-dimensional Hilbert space. So these are your 18 rays. And each of them is shared. So each node in this hypergraph represents a projector. Each edge represents an orthonormal basis to which the projector belongs. So it's a measurement. This projector belongs to 2 bases. So it has 2 measurement contexts in that sense. But these 2 measurements share this projector. So I mean the probability that you're going to assign this to this projector is independent of the context in which it appears. In quantum theory, in operational quantum theory. Now, when you ask that question about whether deterministic assignments, non-contextual deterministic assignments to these guys are possible, then you see that if you try to assign, so the rules are that you have to assign 1s and 0s to each edge such that they sum up to 1, and you can easily check that there are no deterministic assignments. Like if you're attempting a deterministic, So if you're attempting a deterministic assignment, so here black represents 1 and white is 0. So you can do it for all the contexts, but when you come to the last one, you see a contradiction between these two. I'm not sure this is very visible, but yeah. So between this one and this one, like this context requires it to be 0, and this context requires it to be 1 to preserve normalization. So that's the standard proof of the Kochen-Specker theorem. Now there are obstacles to meaningfully talking about experimental tests of the Kochen-Specker theorem, and they have to do with firstly the fact that the Kochen-Specker theorem is a statement about quantum theory and not about general operational theories. It requires you to refer to the Hilbert space structure of the theory and talk about assigning values to projectors. So we need to operationalize that notion. We need to be able to talk about simply about preparation procedures, measurement procedures, transformation procedures, and assign and talking about what probabilities different outcomes occur. So operationalization is needed. Even after you operationalize things, you have to relax certain ideality assumptions that are sort of intrinsic to formulations of the Kochen-Specker theorem. For example, the assumption of outcome determinism is in some sense an ideality assumption because you can only justify it, as I'll show, under when you observe perfect predictability, which I'll define, and so we need to relax that assumption as well. So this is kind of an important slide, even if I'm not able to communicate the rest of this talk. It's important to know that these are the 4 steps we take to go from the statement of the theorem that I gave, the 18-ray statement, to the inequality that I'll write down. So the first step is, again, operationalize the theorem. Second step, do away with outcome determinism, relax that assignment of 1s and 0s, allow for probabilities. The third is that you want to justify outcome determinism. So now you know that the Kochen-Specker argument relies on outcome determinism. So you want to ask under what conditions is that not an assumption, but in fact it can be derived from non-contextuality. So that leads us to an operational restatement of the Kochen-Specker theorem, and this is the most important statement in this paper, which is that the assumption of universal non-contextuality, which is both for preparations and measurements. I'm not defining it because Matt defined it before this. Well, I'm going to define it anyway later. And operational equivalences and perfect correlation. So this I'm going to define operational equivalences as well. Anyway, so the conjunction of these three things leads to a contradiction. That's the Kochen-Specker theorem in our reading of, in our operational reading of the theorem. Now what we want to relax is this guy. So that means that if I want to keep these two, so the hypothesis, so you have to see that the hypothesis about the ontological model here is non-contextuality. This is a fact about the ontological model. These two are facts about the operational statistics. So you want to be able to, so on the other hand, in the original statement of Kochen-Specker theorem, there are two hypotheses. There's measurement non-contextuality and outcome determinism. So you could get rid of non-contextuality, get rid of contextuality by relaxing outcome determinism there. Here we are trying to do away with that. So here there's only one fact about the ontological model. The rest of the facts are you can check in the lab. So this means that when you have, so the way to contend with the lack of perfect predictability in a real experiment is to just rewrite this inference, which is if you're assuming universal non-contextuality and you have experimentally verified certain operational equivalences, then as a consequence you should see a certain failure of predictability, of a certain correlations between preparations and measurements. And if you do not see that failure of predictability, then you have a proof of contextuality, as long as you verified the operational equivalences. So, okay, so an operational theory again is just about preparations, measurement, transformations, and well, I'll only talk about measurements and preparations because these are all prepare and measure experiments. It is supposed to specify this particular quantity, which is the probability for any given effect in the theory, given a preparation. It has to normalize. For a notation, this k given m denotes the event that outcome k occurs when I perform measurement m. Ontological model again is just a deeper description of the operational theory. It's supposed to assign. So let me just go to how they fit together. So the ontological model specifies response functions for every measurement. Firstly it posits a deeper state, a space of ontic states, which is lambda. For every lambda, every measurement effect has a particular response. This thing can be valued between 0 and 1, doesn't have to be deterministic. Mu lambda given p is the sampling from the ontic state space that the preparation makes, and this is the average over the space that gives you the operational probability. So this is the connection between the two, the operational theory and its ontological model. So the other notion we need is operational equivalence. When do we say two procedures are operationally equivalent? When it's just saying that they're indistinguishable when you, so for example for preparation, for measurement events, two events are operationally equivalent if no preparation can tell them apart. If for all preparations they give you identical statistics, that's when you can identify outcomes in two different measurement contexts and say that they're actually the same outcome, that they share, that the two measurements share an outcome. Secondly, the P and P prime are operationally equivalent. These are two preparations. If and only if all effects give the same probabilities for these preparations. So this may be unfamiliar to people only interested in the Kochen-Specker kind of contextuality, but this is what we're going to use to define preparation non-contextuality. It's of the same flavor as the operational equivalence for measurement procedures. Now, what is the context? Here we are using a fairly general definition of a context. The context is basically any distinction between two operationally equivalent experimental procedures. What does that mean? That means, for example, for measurement context, it's a question of, so this is what you talk about in the Kochen-Specker theorem, which is whether a particular measurement is jointly measured with, let's say, M2, M1 is jointly measured with M2, that's an implementation M12, or with M3, M13. So I could marginalize the statistics of 2 and 3 and get like two different implementations of M1 from these two experiments. They turn out to be operationally equivalent if you verified the fact that indeed what you did was the same in the two experiments for M1, and that's also the same as the just doing M1. So this is for example a notion of a context. There are three different ways you can do M1 here. All of them are operationally equivalent. So the distinction between those ways is basically how you're doing them. Here it's with 2, here it's with 3, there it's just on its own. So that's the notion of a context. A second notion of a context could be, for example, different operationally equivalent ways of performing the fair coin flip measurement. Quantum theory allows you to do fair coin flip in fairly non-trivial ways. And so you can read this paper. It's about how to sort of experimentally test non-contextuality. But there, this particular notion of a context plays a crucial role. Then preparation context. For example, different convex decompositions of the maximum mixed state. So this is one recipe for preparing the mixed state. This is another recipe, but they are operationally equivalent. So they are context. They are distinctions which do not make a difference to the operational statistics. And different purifications of a mixed state, for example, could also be a context. Yeah. So this is just a remark that sometimes this distinction, which does not make a distinction in a difference in the operational statistics, necessarily has to make a difference in any ontological model that can be said to do justice to the operational statistics. So that's contextuality in its most general form. Okay, so now operationalizing that hypergraph that I showed you, all I've done here is for every node in that hypergraph, I've made two copies. So instead of like assuming those shared outcomes implicitly, I'm explicitly denoting the operational equivalence between these two events. This is outcome 1 of measurement 1. This is outcome 4 of measurement 6. They are operationally equivalent. Hence, therefore, I'm kind of that fact I'm denoting by this yellow hash region. Now, when you read that original statement, now what does this say? This says that you have a set of 9 measurements. Each measurement has 4 outcomes, and the outcomes, the probabilities of those outcomes share these relationships. Like for this will be always equal to this for all possible preparations. Now, what does that thing say? So now here you're trying to do a value assignment to these guys, and here it's easy to see where the failure of non-contextuality happens. It's here, where you could not this context requires you to assign a value 1. This requires you to assign a value 0, if to be able to complete this assignment. So why is this an operationalization? Because here I'm not because in the first instance the previous hypergraph was about projectors. I was already assuming the fact that it's the same projector shared between this guy and this guy, and therefore it trivially means that the operational statistics will be the same for that projector regardless of the context. But the thing is that when you do not assume quantum theory, then you have to verify this fact. You have to verify that the statistics for this particular effect is the same as the statistics for this effect for all preparations. Okay, so therefore, Kochen-Specker non-contextuality is about these two assumptions. The first is measurement non-contextuality. Again, it's an inference from operational equivalence of two effects to the fact that you represent them equivalently in the ontological model. That is, their response functions are assumed to be the same for all over the ontic state space. And the second assumption is outcome determinism. The fact that these response functions are not arbitrary probabilities, but they are actually 0-1 values. And both of these are assumptions about the ontological model. We want to get rid of this one because we want to test non-contextuality, not this assumption. Okay. So now, how to define this without outcome determinism? So as you can see, the spirit of non-contextuality is the identity of indiscernibles. If you can't tell two things apart operationally, you should not be able to tell them apart in actual fact. So that's the assumption, and you want to test that assumption. So the Kochen-Specker contradiction cannot be derived from measurement non-contextuality alone, because if you relax that assignment of 1s and 0s in that initial hypergraph, then you can construct arbitrary probability distributions over it, and you don't have a contradiction. So how do you fix that fact? So to fix that fact is where you invoke preparation non-contextuality. Okay, now justifying outcome determinism for perfectly predictable measurements. Okay, preparation non-contextuality again analogously is the same thing. Equivalent preparations are represented equivalently. So assumption of universal non-contextuality is both of them together. In quantum theory, we know that preparation non-contextuality and facts about quantum theory imply outcome determinism for sharp measurements. This was proven in this 2005 paper. In fact, so that means that if you relax the outcome determinism assumption, it's preparation non-contextuality that fails for quantum theory. So now we outline how this argument plays out in a general in the 18-ray case, where we're not assuming quantum theory. So what we do instead is that for each of the 36 effects that we had, pairs of which were operationally equivalent, certain pairs of which were operationally equivalent, for each of them we define a preparation. I'm indexing the preparation by the 1, 1, the labeling should be obvious. So for each effect, I have assigned a preparation, and these preparations are chosen such that they, the uniform mixture of these 4 for every edge is operationally equivalent. So P1 to P9 are all, the average preparations are operationally equivalent. Okay, so this is how you, this is a quick argument for how you, maybe, I don't know, how much time do I have?
Wait, you have 8 minutes.
8 minutes, okay, maybe I can go through it. Okay, so, right, so suppose that for all of these nodes, 36 nodes, it's true that, the effect k given mi occurs with perfect predictability for the corresponding preparation ik. So that fact we call perfect correlation or perfect predictability. You can go and measure and check that fact. Now, secondly, you know that, so there are these operational equivalences between these average preparations. And the thing is that for every, so the response function for this particular average preparation is the uniform mixture of the response function, not response functions, the distribution for this average preparation is the uniform mixture of the distributions for the component, the things you're mixing. And because this thing has to be independent of I because of preparation non-contextuality, because you're assuming that they should be represented identically in the ontological model, you can replace this guy with a quantity that's independent of I, which is nu lambda. This is a distribution again over the ontic state space. It just corresponds to the average preparations. Now, the fact that your model has to reproduce this operational fact, the first operational fact, means that this average should be 1, which is that the response function for every effect should average to 1 over the corresponding preparation for that effect, right? Now, this obviously, like from just I mean, if this were not 1, then you in fact, if this were not 1, you can never satisfy this this condition. So therefore, let's just go with that intuitive argument. So this response function xi k given mi lambda has to be 1 for all lambda in the support of this particular preparation. Now this is where preparation non-contextuality comes into play, which is that since this fact is true for all ik, which is what we have to operationally check, and since every lambda in the support of this new lambda appears in the support of some ik, some k for every I, we must have so we must have outcome determinism throughout. Basically, you must have deterministic response functions for all over the support of new lambda. So this you can, if you carefully think about it, you can argue this. Okay, so now in justifying this assumption, which was earlier an assumption but is now an inference from perfect predictability, we have restated the Kochen-Specker theorem in the following manner. Again, this is what I stated at the beginning: universal non-contextuality, operational equivalences, perfect correlations leads to a contradiction. Now this leads to a natural formulation of a non-contextuality inequality when perfect correlation fails, which is this. Like, I'm just reading the same inference again. This is failure of perfect correlation, which means that our non-contextuality inequality has to quantify somehow how that quantity, that predictability fails. So I'm just averaging that the predictability for every effect and every preparation over all 36 nodes. So this is a quantity that we seek to bound in a non-contextual model. So the proof is not that complicated. You just need to rewrite that thing in terms of the ontological model. So the first thing you need to do is you need to take the max over these, the 4 outcomes for every mi. So that is zeta mi lambda. This is the definition of that. Then you can take out, so this becomes independent of k. This thing is the sum over k, and you know that this quantity is independent of I. So this is just nu lambda. This is where preparation non-contextuality comes. And so therefore you have a convex mixture of this guy, and this is less than or equal to the max over the ontic state space of this particular quantity. For every mi, I'm just maximizing over the 4 outcomes for the given lambda. Okay, and this turns out to be 5 by 6. The way you show that it turns out to be 5 by 6 is by looking at the set of probabilistic models on the full hypergraph, basically. Like if you look at the original Edinburgh hypergraph, you can consistently assign probabilities to that thing, and it has a certain number of extremal points. If you characterize that polytope, it has like 146 vertices. It's in 9 dimensions, and the particular vertex that makes this quantity, that maximizes this quantity, is the one that achieves 5/6. there's many of that. So there's like different classes of these vertices. If you compute them, you'll find all the other classes give you less than 5/6. And so this is an example of a vertex. So here the gray circles assign values half, and the blacks are 1 and 0, white is probably 0. And so without loss of generality, you can always think of these 146 vertices as context states, because any space has to assign ultimately probabilities to these measurement events. So noise level. So this is the interesting part of this analysis, which is that trivial POVMs are not a problem in this approach, which is usually a problem with the Kochen-Specker arguments, because trivial POVMs essentially allow you to realize any probabilistic model on a hypergraph, right? You can't draw that neat distinction between classical quantum and GPDs if you allow trivial POVMs like that. So here let's assume that the experiment it follows quantum theory, it's well modeled by quantum theory. Then you can denote this particular quantity as trace over some preparation and so trace over the effect and the corresponding preparation. Let me just so in the ideal limit of when you have just projective measurements, when this guy is a projector, this guy is a corresponding projector, so the preparation is the same as the measurement, you know that this quantity will always be 1, which is that you always realize perfect correlation, and your average predictability is always 1, so which means that operational equivalences and perfect correlation. Again, I'm just reading that original implication differently. If I verified operational equivalences and perfect correlation, then I can again assume. So this is in some sense the operational generalization of the Kochen-Specker argument. Okay. Now, if you consider a depolarizing channel which introduces noise into your preparations and measurements, then let's say this is just a simple channel which just introduces uniform noise, and if you do this analysis, then you see that this probability is this much. The average predictability turns out to be this much. If you're so now consider trivial POVMs. For trivial POVMs, you know that these guys have to be 0, like at least for POVM. Yeah, so this guy has to be 0, which means the product P1 P2 has to be 0, and A is 1/4, which is well below 5/6. Okay, so it's a non-contextual setting. It's not contextual in the way we have studied this phenomenon. So and the non-contextuality inequality is satisfied. On the other hand, the noiseless ideal limit with projectors and pure preparations, you always achieve like P1 and P2 equal to 1, because you're preparing that's the ideal noiseless limit, and you achieve perfect predictability, which is like in some sense the maximal violation. That's the analog of the Kochen-Specker theorem in this operational generalization. So the takeaway, these are the things I want you to take away from this talk, even if you didn't follow the rest of it. Just remember the first fact, which is the operational version of the KS theorem just says that if you verify certain facts about the operational equivalences and facts about perfect predictability, then under an assumption of non-contextuality, you are bound to get a contradiction. You can read this differently, and then you can derive inequalities. This allows us to graduate to a theory-independent non-contextuality inequality from an uncolorability proof of the Kochen-Specker theorem. Now, again, I have to emphasize that this is not a Kochen-Specker inequality, because, as should be obvious, a Kochen-Specker inequality doesn't make sense in an uncolorable hypergraph, because there are no deterministic models in that hypergraph. Okay? It tolerates noisy preparations and measurements, something that's not usually taken into account in standard accounts of the Kochen-Specker inequalities, even in cases where they're well defined. And lastly, no artificial restriction to sharp measurements is needed. The traditional notion of Kochen-Specker theorem is for projective measurements, which are sharp measurements in quantum theory. Here, one option for us was to define a notion of sharp measurements and then prove like an inference from preparation non-contextuality to determinism. We did not take that route. Instead, we just took the route of observing the predictability and justifying it from that, facts about the operational statistics rather than some structure of a general operational theory. Okay, so thank you.